Hello, hi people. So after a long time we are catching up here. Hope your CAT preparation things are going well. So here this video we are about to do a proper math. So we have taken one particular idea and we are going to discuss that. So let's directly jump into the video session. So here, yes, we all know the sum of the first n natural numbers. So it's going to be 1 plus 2 plus 3 plus 4 up to any natural number. The sum is going to be n into n plus 1 by 2. So this follows from arithmetic progression. So we use this formula very frequently, nothing new. Frequently we use this, and we also know how this works. So it's not a very complicated thing to understand. If you want to prove this, we can easily prove this. So we'll go to the proof part a little later. But before that, I wanted to put another question here itself. So what about this one, 1 square plus 2 square plus 3 square up to n square? That is sum of the first n natural numbers whose squares. So sum of the squares of the first n natural numbers. This also we know n into n plus 1 into 2n plus 1 whole divided by 6. So this is fine. This also we know. But have you ever thought of how this works? Or what is the proof behind this? So we'll come across a meme here. So yes, this is fine. I can even tell how this works, or I am ready to learn how this works. But okay, yes, I am avoiding this. I am just going to use this. That alone is sufficient for me. I am not going to think about the proof how it works. If something is complicated, we usually avoid it. So I am just going to use this. As long as it works, yes, okay, I am fine with it. But I am not going to dig deeper, disturb it. Okay, yes. So here we will try to see both of them. So starting from this, we will try to prove this. Then also we will try to prove the next one, 1 square plus n, 2 square plus 3 square up to n square. So this is quite simple. The sum of the first n natural numbers. I am going to take this sum maybe as an expression m. So m is equal to 1 plus 2 plus 3 and so on till n. And the term which is going to be, the last but one term is going to be n minus 1. Right? Yes. Fine. So these are going to be the first n terms. Now we need to find the sum. So what we can do is, we will do a small adjustment here. I am going to rewrite the same sum m in a different way. I am just going to take all these terms, write it in the reverse order. So the last term n will now come here, n. Then last but one, n minus 1 comes here. Then and so on. You will have the next term to be n minus 2 and so on till 2 will come here, because the second term 2 that will come here as last but 1, and the first term 1 here will come here as the last term. So just I am going to reflect as a mirror. I am going to just write the terms exactly in the reverse order. Finished. Now we will do something. We will just add these two equations. 2m will be nothing but. Now we will note something interesting happens here. I will take the first terms of both these series. This is n plus 1. Again here 2 plus n minus 1. This is again n plus 1. Again 3 plus this will be n plus 1. And here this will be n plus 1 until the last terms of these two series, that's going to be n plus 1. So I'm actually adding, we are adding n plus 1, n plus 1, n plus 1. And for how many times is this happening? So this is happening exactly for the number of terms times. Number of terms, there are n terms. 1, 2, 3, 4, 5, 6, we are counting till n. That means there are n times, which means this n plus 1 is added for n times. So 2m is simply n times of n plus 1, and hence m will be n into n plus 1 by 2. That's it. So this is going to be the simple proof that's behind this formula. If I want to do it in a conventional way, this is what we can do. Or I can rewrite it. So whenever we need to find the sum of the first n terms, we can give a notation using the sigma notation. We can give it as a notation. How we can give this is sum of first n terms, n natural numbers, that can be given as sum of all k's. So I am introducing a variable k, and I will make k run from 1 till n. So summation k runs from 1 to n, k, this is what is going to be n into n plus 1 by 2. Now this is an important prerequisite which we are going to use to prove the next idea, which is going to be the sum of squares of first n natural numbers. So this we are clear. This we can do anytime. It's easy to understand also. This we would have done many times also. Even if you have not done using variables, we would have done this with numbers. So simple arithmetic progressions idea. So let's keep this. We are going to use this one to prove the next idea. Fine, okay. How are we going to proceed with this? How are we going to prove this? So we are going to do a kind of a heavy duty math. So properly, carefully we are going to do this. So we are going to do it in an elaborate way also. And this will not be easily following in a sequence. We will not be able to follow this with an arithmetic progression or anything. So we are going to manage writing the terms, rewriting the terms in a comfortable way, and then we are going to see the proof. Let's start this. Fine, okay. Now here we have basically 1 square plus 2 square plus 3 square and so on. So let us take this notation as, here if I want to write it using a summation sigma, I will again make k run from 1 to n, but this time we are going to add the squares. That means we are actually adding k squares. Fine, that's it. So if k is 1, it's going to be 1 square. If k is 2, it's 2 square. K is 3, it's 3 square, all the way till k is n square. So addition of all these is what is going to be what we are going to find. We know this, but we are going to prove this. Fine, okay, yes. Now I am going to take this sum to be sum s. I will name this as s. So s is equal to summation k runs from 1 to n k square. Okay, we will have this in our mind. And also we already know that summation k runs from 1 to n k, sum of all terms k is going to be n into n plus 1 by 2. Fine. N could be anything. Fine, any natural number. Fine, okay, coming back. Now we'll try to rewrite the terms here. So the first term here is 1 square, 1, which is basically 1. Second term is 2 square, which is 4. I am going to write 4 as something interesting follows here. 4 as 1 plus 3. And next is 3 square 9, which is nothing but 1 plus 3 plus 5. So interestingly, each of these terms are going to be nothing but the sum of odd numbers, the first n odd numbers. For instance, my first term is 1, which is going to be the sum of first 1 odd numbers, which is technically 1. 4 is the sum of first 2 odd numbers, positive odd numbers we are talking about. 9 is the sum of first 3 odd numbers, 1 plus 3 plus 5. Suppose you take 16, the fourth term, that's going to be the sum of first 4 odd numbers, 1 plus 3 plus 5 plus 7. That's an interesting pattern we have. Now in this sense, what can we tell about the last term n square? This should be the sum of 1 plus 3 plus 5 plus 7 and so on. The sum of first n odd numbers, and the nth odd number will be nothing but 2n minus 1. So we are going to add all these to get our sum. Now LHS, if we add 1 plus 4 plus 9 plus 16 all the way till n square, that is going to be our sum, and we have notated it using S. So we will write as S. So S means addition of all this. It's going to be equal to, now come to the right hand side, let's play this very carefully. Now we have 1 plus 1 plus 3 plus 1 plus 3 plus 5 plus 1 plus 3 plus 5 plus 7 and so on till this. Now we'll just split it. Take this, all these ones. Now how many ones are there? 1 plus 1 plus 1 plus 1 plus. Now we have so many number of ones. How many ones are we counting? There are n terms, that means there will be n ones. So there are n ones. Fine, okay, done. Next, we'll count all the number of 3's. How many 3's are there? There are number of 3's, but not only in the first term. That means out of all these n terms, we are counting n for n minus 1 times. That means the first term alone you don't have a 3, and we have 3 available in all the remaining terms, which means one term less than n, that means n minus 1 times we are counting 3. Good, fine. Next, what about 5? N minus 2 times we are counting 5, and so on and so on. And how many times are we counting 2n plus 1? Just one time, and one time of 2n minus 1. I hope you are able to understand this step. This is slightly crucial, but still follow this very carefully. N times of 1, then 3's, 1 lesser, n minus 1 times of 3, 1 lesser, n minus 2 times of 5, again 1 lesser, n minus 3 times of 7 and so on. It come like this. last 2n minus 1 will be counted exactly once. That's what we have written here. Fine. Okay, alright. Done. Now what next can be done? Again we are going to do a kind of adjustment with this. S is equal to, now I am going to do again a small kind of adjustment. So look this very carefully. I have n minus 1, n minus 2 and so on till 1. So these are my terms here which I have. They are getting multiplied with 1, 3, 5, 7 and so on. Now these are all odd numbers. We will come deal them a little later. We will now address this n minus 1, n minus 2 and so on. Okay, fine, yes. How can we rewrite them? I am going to rewrite them slightly in a different way. So what am I going to do is, I am going to take this n as n and then minus 1 plus 1. Will it work? So why are we doing this? Why do we need to do this? We have a reason. I am rewriting this n as n minus 1 plus 1. Okay, fine. Next, this is 1 times, so let me write that 1 also multiplied with 1. So we should not be leaving that also. Okay, then fine. Now what about this n minus 1? This we will rewrite it as n minus 2 plus 1 times of 3. Again continue this n minus 2 we will write it as n minus 3 plus 1 into 5 and so on. That means I am going to follow a kind of uniformity. That's why I am doing this. This n is written as n minus 1 plus 1 so that these two gets cancelled and gives you n back. This n minus 1 I am rewriting it as n minus 2 plus 1 so that this will cancel back and give you back minus 1 and so on. N minus 3 plus 1 will give you n minus 2 and so on. And finally this 1 also follows in the same pattern, comes in the same pattern. Now how can we rewrite that 1? That also we will manage to write as n minus n plus 1. Okay, yes, into 2n minus 1. We don't have much space there. Fine, okay, yes. Success, we have succeeded here. Now I am going to again come back to I'll take a fresh slide here because like the work is too lengthy. You need to be carefully doing. So even if it takes time, no problem. So if you have patience, you also be carefully following. Yes. S is equal to. Now once again, we left here. So I am going to try to segregate the terms. Now look here carefully. N minus 1 plus 1, n minus 2 plus 1, n minus 3 plus 1 and so on, n minus n plus 1. This is what we have. So I am again going to manage the terms in the sense, I am going to rewrite it as n plus 1 minus 1, n plus 1 minus 1 times of 1, then plus, what about the next term n plus 1 minus 2, I am just rearranging the terms, n plus 1 minus 2, n plus 1 minus 2 times of 3, that is going to be 3. Then third term will be n plus 1 minus 3 times of 5. I hope now you are able to follow the pattern very carefully and so on till the last term is n plus 1 minus 1 into 2n plus 1. The last term would be n plus 1 minus n into 2n plus 2n. It's going to be 2n minus 1, correct? Yeah, 2n minus 1. Fine, okay. Now we have done this. What are we going to achieve here? Yes, we have got clearly. Now S is equal to. Why are we struggling here is, I am going to now rewrite this in terms of a summation. Of summation, I will make k run from 1 to n and look at this very carefully. Now all these terms, what you see first in each term, they are all actually products of two terms. In those products, see the first term, it's actually of the form some n plus 1 minus k. So that when you carefully place the value of k from 1 to n, you will be getting each of these terms. If k is 1, it's the first term, n plus 1 minus 1. If k is 2, it's the second term. If k is 3, it's the third term and so on. We are getting this multiplied by, now we will worry about the second term. This is 1, 3, 5, 7 and so on till 2n minus 1. That means this is nothing but the nth odd number. That means since we are writing in terms of k, it's going to be the kth odd number, which is 2k minus 1. Simple and interesting, right? So now we have succeeded in writing this. So S, which was of this form, so how? Previously S, which was of S is equal to 1 square plus 2 square plus 3 square till n square, is what now became, we have rewritten it in the form of this. K runs from 1 to n plus 1 minus k into 2k minus 1. Okay, yes. Now we will distribute this inside and try to simplify. Fine. Okay, yes. So one half part we have succeeded, the other half let's do it even more patiently. Okay, I'm going to continue this in the next slide. Fine, yes. So this, let me try to distribute. S is equal to k runs from 1 to n. We'll open a bracket. Now I'm going to multiply. Now this is n plus 1. Now I'm going to take this n plus 1 entirely. N plus 1 minus k into 2k minus 1. It means like I have two terms here. I'm going to multiply this. N plus 1 into 2k. N plus 1 into 2k will give you 2 into n plus 1 into k. Correct. So this into this will give you 2 into n plus 1 into k. So I'm going to write that 2 into n plus 1 into k. Okay, yes. Again, n plus 1 into minus 1 will give you minus of n plus 1. This will give you minus of n plus 1. Okay, yes. Coming back. Now this into this, done. This into this, done. Next, I'll do minus k into 2k. So minus k into 2k would give you minus 2k square. So note down that minus 2k square. And finally, one last term, we'll do that also. So minus k into minus 1, that's going to be plus k. Yes, plus k. Success. Wonderful. Okay. Yes. Now we'll bring the summations inside, because we have got 4 terms here. We'll carefully bring the summations inside, and remember, now our summations is only in terms of k. Our n is like a constant. Right? Yes. So that means s is equal to. Bring it to the first term here. So you'll be having 2 times of n plus 1 of summation k runs from 1 to n k. So once I bring the summation inside, I apply this to each of these terms inside. For the first time I am getting this. Why are we taking this 2 of n plus 1? It's a constant now. It doesn't matter. So this is not going to anyway affect my this summation. So I am going to keep this one k terms alone inside. Whichever constants I feel I have, I will be placing it outside. And then next is minus of n plus 1. Again n plus 1 is a constant for us. Summation k runs from 1 to n. Now what do we have here inside? I will only have a 1 here, because for the entire n plus 1 if I have taken outside, I will have it like a minus 1, which is what will be staying inside. Right? Okay. Next here, I have minus 2k square. Only k square will be there inside the summation. 2 comes out. Minus 2 times of summation k runs from 1 to n k square. And finally, one last time, summation of plus k runs from 1 to n k. Good, super. Done. Nice. We are proceeding carefully, properly. Now, yes. S is equal to 2 times of n plus 1. Now, I hope you remember this. K runs from 1 to n, summation k. This is nothing but the sum of first n natural numbers. 1 plus 2 plus 3 plus 4 up to n. This we already know. This is what we have initially proved at the beginning. So, this is nothing but n into n plus 1 by 2. Great. Minus here n plus 1 into. Now what do you think about this? Summation k runs from 1 to n 1, which means you are going to add only the term 1 for n times. 1 plus 1 plus 1 plus 1 plus n times. This is simply n. Okay, yes. Minus 2 times of. Now what do you think about this? Summation n runs from k runs from 1 to n k square. Now what about this? This is nothing but s itself. This is what is our s. So that means I am going to replace this with s itself. Actually telling, this is what we are fighting and finding for. So this expression is what is what? This is what we are trying to find. So this is going to be s. I am going to rewrite this as s itself. 2s. And finally one last time, this is going to be again, this is same as this. Sum of first n natural numbers. and this is going to be n into n plus 1 by 2. Okay, going great. Now we need to find the value of s. Let's try to keep all the s terms to one side. So this becomes 2s minus 2s. When it comes here, it becomes 3s. So 3s is equal to. Now we'll try all possible simplifications. We'll be getting 2 and 2 getting cancelled. What else can be done? This has already this came here. There we still have nothing got to cancel. We have got nothing. Now the only thing is we can take something common. We'll factor out something common from the remaining 1, 2, 3 terms. Remember, this came here. This has got nothing to do here. Now we can factor out some common terms. Interestingly, I have an n into n plus 1, n into n plus 1, n into n plus 1 everywhere in common. So I am going to take that n into n plus 1 common outside from everywhere. So what will I have inside? What I will be left with inside is, here I will have an n plus 1, here anyways minus 1, and here I will have a plus half. Wow, super nice. So now this is nothing but n. Let me try simplify this step here itself. N into n plus 1 into. Now what about this? This is anyways plus 1 minus 1 getting cancelled. We will have n into 1 plus n plus 1 by 2. So n plus 1 by 2 can be simplified as 2n plus 1 by 2. Done. Super. So n into n plus 1 into 2n plus 1 by 2. So finally 3s is this, which means our s is going to be bringing this 3 there to the denominator. We will have our overall answer simplifying to be n into n plus 1 into 2n plus 1 divided by 2. 3s are 6 and success. So this is what is our summation of squares of first 10 natural numbers. Sum of squares of first 10 natural numbers. So sum of 1 square plus 2 square plus 3 square and so on till n square. So which is what we call it. So like we should properly rearrange and tell it as sum of the first 10 natural numbers. The sum of first 10 natural numbers is going to be simply n into n plus 1 by 2. But here all we are finding is 1 square plus 2. We are squaring it and then adding it up. So that's going to be this. So clearly this gives you the formula, the proof. Yet there are many ways to prove this. So this is not the only way. If you are using advanced topics like permutation, combination, combinatorics, we have got some high level methods to solve and get the answer to prove this formula. But still, like, since we are dealing with the basic arithmetic progression ideas, so whatever we have learnt just in the learn curve, we are taking the help of those elements and proving this. So yeah, hope you would have enjoyed this. So maybe in upcoming videos we'll come with some other interesting discussions. See you there. Thank you so much.
Hey, hope this video was useful. For more useful content, sign up with 2am for a 40-hour free course with us. All the best.